I hope in the last two examples you realized how helpful that table can be for solving these problems. But a lot of times you're not going to be given a table. Like in this problem where you know from a survey from the CDC, they were asking respondents if they had learned something new about a health issue or disease from a TV show in the last 6 months. So we're going to let L be the event that the randomly selected adult reports having learned something new about a health issue or disease from TV. And then we're also going to let F be the event that a randomly selected adult female or adult American is female. So we know that the probability that they had learned something from TV was 0.58. We know that the probability of female is 0.5, so they had the same number of males and females. And we know the probability that they were both having learned something from TV and female is 0.31. How would we figure out the probability of L or F? So how do we tackle a question like this? Well, there's a lot of different ways, but what I think you'll find to be the easiest is to create this hypothetical thousands table. So we don't know what the sample size is, but the thing is with probability here, it doesn't matter. We're just looking at the proportion. So I'm going to just decide that there's 1,000 people in this group. Now, why 1,000? 100's too small, and 1,000 is easy to multiply. If you pick any other number, you're going to have weird numbers. This just keeps your numbers a little easier to deal with. Most of you will actually be able to multiply these in your head without having to get a calculator. Now, it doesn't matter if you put L on one side or F on the other. It doesn't matter where you put it. So I'm going to put L in one row and then not L. That's going to be everybody else. And then we have female and not female. What do we know right now? Well, we know that half of this 1,000 is female. So here we actually know the total number of females. We're going to put that in the total. We know the total number of people who learn something on TV as 0.58. You multiply that by 1,000 and you get 580. Those gave us totals. What else do we know here? We know that the L and F group is going to be 0.31 for the probability, and that's going to be 310 people in our hypothetical 1,000 table. But where does that go on our table? Where do you have both females and people who learn something on TV? And that is right here in this first box. So whatever information you're given, you'll be able to figure out where it goes in the box. And now you're just going to be working backwards using subtraction to figure out what the missing values are. There's 500 females and we just accounted for 310 of them, so that leaves 190. If there were 500 females, then there's 500 not females. If we have 580 people who learn something, we've already accounted for 300 of them. So I'm going to take that 580 and subtract the 310. Okay, we're just making this table where the numbers work out. And so now we're getting some information about that not female column. So take 500, account for the 270, and that leaves 230. And then the last one, we've accounted for 580, and so that leaves 420. You could have also done that by adding across this time the 190 and the 230. So with just a little bit of work, we now have a table, and so we can answer this question, what's the probability of L or F, by taking the L, all of those, and then the rest of the F. And so this probability is going to be 310 plus 270 plus 190 divided by 1,000. And so here's why it's okay that we just made this hypothetical 1,000 table, because now we're just going to divide it right back out, and we have 770 over 1,000, and as a decimal, that's 0.77. Let's do another problem where we look at creating one of these hypothetical 1,000 tables. We have a survey of adults aged 18 to 50, and the information we have is that they're 18 to 29, if they have a tattoo, and if they have a tattoo or are aged 18 to 29. The question we want to answer is, what's the probability that the person has a tattoo and is aged 18 to 29? So let's make our table. So we're going to have a total of 1,000. And we'll have tattoo and not tattoo. And I'm going to make this Y for young adult and not Y. So we know that 18 to 29 is 50%. So that means 500 of our sample are young adults, which tells us that 500 are not young adults. Then we know the probability of having a tattoo. That's a total value. So there's going to be a total of 0.24 times 1,000, or 240 people with a tattoo. Well, that then tells us that we can take 1,000 and subtract 240, and we see that 760 people in this group did not have a tattoo. Now, this next question, this one, the or question can be a little bit trickier. We know that 0.56 are tattoo or young. So they fit in either of these three. If we were to add up those three boxes, it would add up to 560 for this case. So how do we know where to put them in the three boxes? Well, we don't right now. But here's the thing. Do you guys see that I left off exactly one box? Everybody who's not in that probability is going to show up in that other box. So with the and problems, you were given the intersection of where they both were true. For this union, this or question, really, we knew where they both were not. So we can do 1 minus 0.56, and that gives us 0.44. And so I now know that there are 440 people in that yellow box. Now I can work backwards. 760 minus 440. There's 320 there. 500 minus 320. I get 180 here. And 240 minus 180, I get 60. Now I have my whole table. And if I want to know the probability that a person has a tattoo and is a young adult, I'm looking at these 180 people out of the total 1,000. And so if I do that division, I get a probability of 0.18.